to the last session of this conference, and we have the 4 speakers. The first talk is on routing games in the wild, efficiency, equilibrium, and regret by Barnabé. Thank you.
Hi, good afternoon, everyone. Thank you for staying back. We definitely lost some people. For those who travel from Hello. 1, 2. Yeah, I can hear myself. Okay. So I want to take you to Singapore for a large experiment that we conducted there. And I want to tell you a bit about the results that we have and the questions that we've asked from the data. This is joint work with my advisor, Georgios, who's sitting right there, and Francisco, who's still in Singapore. So we love congestion games in this community, and the reason is that they are general enough that the model is powerful, but they're also structured enough that we have a lot of very nice results. 3 of them, and perhaps the 3 major ones, is that dynamics converge and the system reaches a stable point. Some learning dynamics, such as no regret, they tend to converge fast, and we have guarantees on that. And the resulting system performance is near optimal. These are the results that we know of price of anarchy. And what we want to ask today is how do these results translate in a real network? And we're going to answer this question from data, real data that we collected from people in Singapore. So this is the content of the talk. First, I will introduce the data set and how we collected the data. And then I will ask these 3 questions and give you some answers. We'll first look at the regret of the agents to see if they have low regret and if they perform a game theoretically correctly. Then we will look at the traffic quality and ask if it's close to any measure of optimality. And at the end, I will tell you if the network is at equilibrium. So first, the data set. It was a very, very large data collection. Over 80,000 students took part in the experiment over the course of a year or so. Here's an example of 2 happy students. They were given one of the sensors that are pictured in the middle. And these sensors are quite powerful. They are able to log their geographical location as well as a bunch of environmental factors, such as the temperature or the humidity. And that they do every 13 seconds if the beacon is able to record it. We have a lot of data, but we've actually kept only the really high quality data. So this reduced our sample to about 15,000 students. The data set that we're particularly interested in is the data set of the morning trips of the students. So you have to note that none of the data in the study was reported by the students. We don't know where their homes are, where their schools are, and we also don't know which mode of transportation they are using. But all of this we're able to infer from the data itself. So the trip we get from a rule-based algorithm. We just check what is the time they are at home, what is the time they are at school. And for the mode of transportation, we're able to discriminate between a car, train, or bus, and we do that using some machine learning methods. And there is a bit more detail in this paper from one of our team. This is a map of Singapore, and the yellow nodes are the schools, while the red ones are the homes of the students. A word on the representativeness of the sample. Of course, we haven't measured everyone. As it's an empirical experiment, we can't survey all of Singapore, but it's a pretty representative sample for the following reasons. On the left, you can see the density map of Singapore, and on the right, you have the locations of the homes of the students. And you can see that they match pretty closely. So geographically speaking, at least our sample is not too biased. The last chart shows you the separation between students using private transportation and students using public transportation. This ratio is about 40% to 60%, which in fact correlates really well to what is measured in practice all over Singapore. On to the first questions. I'm going to try and check if the agents have low regret. What do I mean by regret? Of course, in computer science, we have a traditional definition, which is that we look at the average cost incurred by a series of decisions made by the agents, and we want to compare that to, in hindsight, what would have been the best fixed action I could have taken. For us, it's very difficult to get something like this because the number of available routes to go from the home to the school is of course very large. It's very difficult to capture what was the traffic condition at every point of the experiment. So what we do is that we introduce another notion which we call the empirical imitation regret. And how we compute it is quite simple. We look at my travel time, and I want to compare that with the travel time of students that live in my neighborhood and go to the same school, use the same mode of transportation, and live around the same time. To do that, we use a clustering method, either by grid or by circles, to check if the homes are in the same neighborhood. So my regret will be how long I've traveled minus how long the fastest student traveled. Okay? Please stop me if you have any question or if I'm being unclear or you want to know more about the data. Correct. It's geographical location. So either we look at the grid and we say that students that fall in one cell are in the neighborhood and the grid size is about 400 meters by 400 meters. Or we use a more advanced clustering where we look at circles. So we group the students, but it's geographical clustering. So the result we get is that the empirical imitation regret is quite low. On the right, you can see the chart here. We plot the complementary cumulative distribution function. And you can see that for an average trip duration in our population of 28 minutes and 30 seconds, we have a median regret of about 4 minutes and a mean regret of about 6 minutes. So this is quite low. Additionally, we can see that 80% of the clusters have less than 22% of average multiplicative regret. And by that, we mean that on average, the trip of the student is not 22% longer than the trip of the fastest student in the same cluster. So the regret is low. Of course, we've done some sensitivity analysis. One thing that we've tried to play with is the size of the clusters. If the clusters are very large, we get a lot of students to compare with, but of course we lose in precision because they are not comparable students. If the clusters are too small, then we won't have enough students to compare with. But you can see that the results are not too sensitive to the cluster size. So we've found that the agents have low regret, and we've defined this notion of empirical imitation regret. And now we'll move on to the second question, to know if the traffic quality over Singapore is close to optimal. Any questions to this point?
For example, like if you take a taxi, which will be much more expensive than MRT, right?
Right. So the cost function here is really based only on the latency, so how long the students take to go from their home to their school. You can, of course, add several other measures, maybe the comfort or the price of your trip. This is not something we've looked at in this study, but that we plan to look on later. Thank you. So we all know this example, and we've seen it a couple of times by now, but I'll go quickly through it. This is the classical Pigou example. We have a unit demand wanting to reach the green node to the red node, and they have the choice of using either a variable congestion link or a constant congestion link. And we know that at equilibrium, everybody will take the upper edge, and the social cost will be 1. But at the optimal, a central planner would like to split the flow between the two edges, split equally. And at this point, the social cost will be equal to 3/4. This result we know as the price of anarchy, which measures the social cost of the worst equilibrium to the one of the optimal state. And the price of anarchy has gone from this first result of being independent of a network topology, and this is Rovgarden in 2002 and Tardos, that found this tight bound and made the bound also for different classes of function. And then progressively it started getting more results and being more robust. For example, we know that it generalizes well to no regret learning. This is Bloom in 2006 et al. And we also know that for atomic games, where the players become very small, the bounds tend to look alike to the non-atomic case. And finally, we also know that the price of anarchy generalizes quite well to dynamic populations. This is a recent result by Licorice et al. So this is sort of a theoretical framework that we are able to work in. Okay. A recent paper by Zhang and Pascalidis tried to approximate the price of anarchy for a real network, which is the Boston one. But the method that they used and the data that they had was a bit different. And for one thing, it was pretty computationally intensive to do, and they assume also that the population is at equilibrium. But for us, we want to do something simpler. We want to use the data that we have and collect some additional data, and we'll use that to compute what we call the stress of catastrophe. So the stress of catastrophe is very simple. On the numerator, we just have the cost of all the recorded trip durations. And the denominator will be the cost of the free flow trip durations. So what we mean by free flow is we want to look at if no one was on the road, how long would it have taken me to go from point A to point B? If I went from the airport to here last time in something 30 minutes, and I believe that now I will take an hour and a half, meaning my stress of catastrophe will be 3, because I will take 3 times more in a congested regime. So what the stress of catastrophe does is that it measures the system stress. And I want to show you now that the stress of catastrophe is actually an upper bound to the price of anarchy. And this is a very simple result to get. We know that for every trip, the cost in a no congestion regime will of course be smaller than the cost of the trip in a social optimum. So we are able to reverse it, and we get that the price of anarchy is in fact upper bounded by the stress of catastrophe. But if you see, the cost here is not exactly the one of the price of anarchy. It's not the cost in equilibrium. But this works for us if our empirical imitation regret is low. Because if the regret is low, we know that we can extend these bounds to the price of anarchy. Okay. Any question? So we know this curve. This is on the x-axis the demand, and there's a really nice paper that will be introduced right after mine that says under very weak assumptions the POA goes to 1 when the demand increases. And this is a quite natural result. Imagine a system that is completely gridlocked and think, okay, what can a central planner do to make this system better? There's not much room to improve. On the other hand, the stress of catastrophe will keep growing as more cars are added into the system. So we're able to measure precisely how stressed the system is. And from the upper bound that we saw earlier, we also know that if our stress of catastrophe is low enough, we also know that the price of anarchy will be low. So one thing the price of anarchy doesn't do really well is quantify the effects of the tragedy of the commons. You can see the road network as a shared resource that agents enter and use, and maybe one additional agent will not make the system perform really worse, but since everybody enters the system gets very stressed, and the overall social cost is really low. So you can see on the picture on the left, there's really 2 ways to look at the situation. Either you're happy because the price of anarchy is 1, and that might be fine, but here your stress of catastrophe is 10, so you could also say that you're not very happy because the system is very stressed. So this is what the stress of catastrophe wants to measure here. You could, yeah, it looks like a car park. It's a gridlock, something where people are not moving. Good point. So how do we obtain this free flow duration? I told you that we want to do that because we have the data, and this is a very simple data to obtain. What we did is we queried the Google Directions API in multiple periods of time, and with a setting to ask for an optimistic travel time, and it returned several traffic conditions to us, several travel time, and we used the minimum. So we want to ask, okay, what is the best possible trip I can ever do if no one was on the road? This is for car users. And for public transportation, it's pretty much the same thing. We've queried the directions, and we've removed any waiting time. So it's like a blue sky ideal scenario. You get all your trains and your buses right away. Now on to the result. We find that the price of anarchy bounded by the stress of catastrophe, so that the stress of catastrophe we estimate at 1.34, which should be surprising because it's really close to 4 by 3, and it's kind of a nice result. This we obtain when we consider both the private and the public transportation users. So we have both people in cars and people in buses and trains. What is a bit surprising is, I mean, not so surprising, is that once we remove people using public transportation from our sample, the stress of catastrophe is much higher at 1.86, which makes sense because cars congest the network more. And this is a thought experiment to put these numbers into perspective, devised by Georgios. Think that all the cars in Singapore are photon cars, and they're made of light, so they can overlap onto each other. So congestion doesn't matter for them. And now what this tells us is that even if the cars were made of photons, the traffic network in Singapore could not improve by more than a factor of 2. So it's quite a nice result. It's pretty good for Singapore, I guess. And finally, I will move on to my last question. Is the network at equilibrium? This is a pretty natural question we want to ask of any system. We want to know if it reached a stable point. The context in which we're going to ask that is that we want a strong stability. We want to know if people make consistent decisions from one day to the next. So we want to know at the individual level, do they use the same routing decisions? For example, we are interested in what happens on the top case, while on the bottom case here, maybe the flows are the same, I mean the level of the flows, but the compositions of the flows are different. So this is not what we want to know. We want to know if we're in this case. And to study that, we need temporal data. And this temporal data, we have some of it. The students carry the sensor for up to 4 days. So in our data set, out of 15,000 students, almost 2/3 have 2 or more morning trips logged in. So we're able to make some estimations over this sample. What we find is, in this sample, 65% will reuse the same mode throughout the experiment, so across the 2, 3, or 4 days, while 35% do not. And for these students who use the same mode of transportation, 94% actually use the same route in every day of the experiment, which seems to make sense, but it's always a nice verification to have. Okay. To conclude and to recapitulate the 3 questions that we've asked, we first look at the individual efficiency. And to do that, we've defined this empirical imitation regret, and we found that it is low, which is good because it's consistent with the game theory interpretation. If my neighbor was going 15 minutes faster than me to school using the same means of transportation, I would ask myself the question of, should I change something about my decision? We've also looked at the global efficiency, and to do that, we've defined the stress of catastrophe, found that it upper bounds the price of anarchy, and estimated it at 1.34 for all modes and 1.86 for the cars. And we find that it's comparable to theoretical constants, and in fact, a bit smaller. Usually in transport literature, the latency functions used to quantify the network are the quartic functions. And for this, we find that the price of anarchy is something like 2. So we find that it's a bit smaller here. Finally, we found that the network is stable and that the routing decisions are pretty much consistent in the data set. So 3 nice results that sort of reassure us that the theory is not going all wrong. But finally, these are some more questions that we would like to ask. We've seen that the public transportation has a huge effect on the stress of the system. Public transportation users are very much a different type of players. They may not have access to the same network at all. So we want to ask if perhaps different models could be found to understand this result. A second point is we want to look at the fairness, and we want to investigate this relationship between the efficiency of the system and how fair the system is. This is an ongoing work that we have with Koutsopias and Papadimitriou. And finally, an interesting question is the relation between the price of anarchy and the stress of catastrophe. So we want to know if we are in maybe a system that is efficient but overstressed, or the opposite. To go back to the curve, we want to know if we're on the left side, so a light congestion, or on the right side, a heavy congestion, which will also be talked about by Riccardo. Thank you. And this is also, we are hiring, and if you have any if you want to come to Singapore, you should definitely email August about it. Thank you.
So we have time for 1 or 2 questions. Yeah.
So thank you for your presentation. About stability, you stated that the students are at equilibrium. I was wondering if during the first days of school you observed like a convergence, or did they start out straight at equilibrium?
So the experiment was conducted in like March, May, different time periods of the year. So it's not necessarily the first days of school. Like I think in the experiment, the students have gone to school several times, have probably they know the way. So we look at the system maybe in a steady state. Yeah. Sorry?
Like you said, 94% consistently use the same route. Like
yes.
Right? So is this consistent with the wardrobe equilibrium? What it would have said theoretically?
So wardrobe equilibrium just tells you the level of flow.
Yeah.
It doesn't say that people will use the same route. So in a sense, it's consistent for individual decisions that you are.
At least is that proportional is correct? Like what proportional of the traffic goes in particular route? Is it inconsistent with
so
what
you mean
wardrobe?
can we compare the measurements we have with a wardrobe? So this is the approach that the other paper took. So for that you need to know the network of routes, and you also need to know the cost functions on your links. Yes. So we don't actually estimate these. So we don't know the equilibrium flow. What we're able to say is that people make the same decisions and they have low regret. So we believe that the system is at equilibrium. But this is done without estimating cost functions. This is something we want.
Okay, so let's thank the speaker once again.
Yep. Try. Does it work?
Okay, so next talk is on when is shellfish routing bad.
Thank you. So this talk is about when is shellfish routing bad, in particular with a perspective of light and heavy traffic. First of all, I want to thank you, my co-authors, Roberto Cominetti from Universidad Adolfo Ibáñez from Santiago in Chile, Panayotis Mertikopoulos from CNRS in France, and Marco Scarsini from Lewis University in Rome. So I don't think I have to explain you why studying congestion is important. I'm from Rome, and this picture doesn't look that different from what I experience every day commuting from home to work. And in my experience, from what I saw these days, not also that different from what you experience in Bangalore. But so at best, congestion means that you are in late for dinner, but it may also be translated in incidents, stress, damage to the environment. So it's meaningful to be studied. And I also want to mention, the famous example of congestion that was verified in August 2010 in China, Highway G110, where due to traffic jam, a queue of 100 kilometers was created, and people were stuck in their vehicles for 5 days. And they were not be able to drive more than 1 kilometer per day. So, ironically, the congestion was not created by weather or a natural disaster, but just because too many heavy trucks were transiting on the highway because they were carrying supplies to build facilities to ease the congestion themselves. Okay, so the question now that we want to address in this talk is, what are the causes of the congestion? So to do that, let me introduce actually what is the model that we want to study. We have a network that is a directed multigraph G with a set of vertices V and a set of edges E. I'm in a multigraph because we allow multiple edges between any pair of vertices. In the network, we allow many OD pairs. So for example, here we have one OD pair that is described by O1 and D1, and another one by O2, D2. And different traffic flows traverse different OD pairs. So the capital PI will describe the set of paths that joins each different OD pair. And the routing flow of FP will describe how much traffic is traversing each path. Okay? So since each path is belonging to just one OD pair, FP will be the traffic generated by that OD pair that is traversing the path P. Given this routing flow vector, we can compute easily how much flow is actually transiting on each edge in the network, simply summing up all the flows of the path that actually owns the edge E. And having the load for all the edges in the graph, we can compute what are the latencies on those edges, right? So we have cost functions associated with the edges, and CEXE will represent the latency that each infinitesimal traffic amount experience when he will traverse the edge E. Okay? The latency function that we are considering are non-decreasing, non-zero, and continuous. So no assumption. Given that, you can compute which is the cost of each path, simply summing up the cost of the single edges that compose that path, and all those ingredients formalize our non-atomic routing games. So we have a game, and in this class of game is well known how the equilibria look like. They are described by the wardrobe first principle that essentially states that at equilibrium, all the utilized paths have the same cost, and that cost is higher than the paths that are not used. Okay? And this set of equilibria can be fully characterized by this minimization problem, where the objective function is simply the sum of the primitives of the cost functions for each edge in the network. So we have a clear understanding of what the equilibria are, and we also have a clear understanding of what is the optimum. Optimum is a different minimization problem, where the objective function is simply the minimization of the total cost of the network. Okay? So you may notice that wardrobe equilibrium and social optima are both solutions of minimization problems, but with different objective functions. So you may guess that in principle there is some gap between equilibrium and optimum. And indeed, this gap can be measured by the price of anarchy that was introduced by Kotsopias and Papadimitriou in 1999, and measure how much, what is the inefficiency injected in the network through the selfish behavior of the players. The price of anarchy is represented by the ratio between the cost at equilibrium and the cost at the optimum, and is greater or equal to 1 by definition of optimum. And is equal to 1 if and only if all the equilibria are efficient. Since price of anarchy has been introduced, a lot of work has been done to understand if we can upper bound the price of anarchy for different class of routing games. Let me mention just a few of them. Riccardo and Tardos in 2002 found the upper bound for a routing game where the cost functions are affine functions, and in this case the upper bound cannot be greater than 4/3. And in 2003, Riccardo generalized this result to a network with polynomials of degree at most d, and in this case the upper bound is d over log d. All those results are independent of the network topology and hold for any number of OD pairs that are in the network. So you may see from the last result that price of anarchy can be arbitrarily bad when d goes to infinity. And actually, those bounds can be realized if you, with specifically tuned networks. Okay. So the problem is that those bounds having networks that actually realize this bound is it's not complicated, but requires some manipulation of the network. And in real world, we have networks that are fixed and demands that varies over those networks. So the question that we want to answer is, how bad is selfish routing in practice when you cannot just change the network as you want? This question was also tackled by Yahoo et al. And O'Hare et al. They studied different typical urban networks like Boston, London, and New York. You may see that the plots of the price of anarchy in those networks look rather different, but they share some aspects. At the beginning and at the end, the price of anarchy converges to 1, while in the intermediate region, the curves have some fluctuation that depends actually on the network topology and on the other aspect of the network itself. The effectiveness of price of anarchy in the empirical, in the real world is also been studied by Monnot et al., and we heard about that in the previous talk. So the first question that we wanted to answer is it always true that the price of anarchy converges to 1 as the demand grows to infinity or decreases to 0? Or is it at least true that the price of anarchy has this behavior when there is a single OD pair in the network, or if we have a parallel network, or if we have a nice cost function like convex cost function? So we were able actually to answer all those questions, and the answers were no, 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 and no. Indeed, we designed a very simple network with just 2 vertices and 3 parallel edges, just a single OD pair network, with convex cost function, in which the price of anarchy is always bounded away from 1. Okay? So it's always inefficient. And this is true because you can observe it because the price of anarchy in this case has a periodic behavior on a logarithmic scale. So you have the full plot of the price of anarchy there. So next question is, what's wrong with this example? Why the price of anarchy is not going to 1 here? So you may look at the cost function, and they are convex, but they are not that nice. So the problem here is that they scale very irregularly along with respect to the argument. So the problem is that they have very dense oscillation when the traffic is light, and very wide oscillation when the traffic is heavy. And this creates this pathological situation. Okay? And the price of anarchy and the periodic behavior of the cosine and the sine give us, together with this pathological behavior, the price of anarchy always greater than 1. So what we did is to understand what are the weaker conditions that remove this pathological behavior and allow the price of anarchy to go to 1. So we fix on networks that do not allow that. In order to do that, we focus on 2 different cases with different perspectives, the light traffic case and the heavy traffic case. In both cases, we want to remove this pathological behavior. So how can we do that when we have light traffic? Is simply focusing on cost functions that allow this limit to exist and being positive. Okay. What does it mean? It means that the cost function of our network has to behave like a monomial plus some other terms that are negligible when the traffic goes to 0. And it is not restrictive if you think about it, because many cost functions fit in this, realize this assumption. Indeed, polynomials did, and any real analytic function did. Any function that can be approximated by Taylor series attain this assumption. So the first result here is that for any single OD pair network with cost function that satisfy the hypothesis that I mentioned before, the price of when the traffic goes to 0, the price of anarchy converges to 1. In particular, in any network with polynomial cost function, we have this behavior. Now, when we have heavy traffic, the situation is slightly different, but not that much. We changed the assumption in order to exclude the pathological behavior of the cost function, and we used the regularly varying function to exclude that behavior. Let me explain. first, what is a regularly varying function? It's a function introduced by Karamata in 1930 and widely used in probability and extreme value theory that state that a function is called regularly varying function if that limit is finite and non-zero for all x greater or equal than 0. And our idea is not to restrict to networks that actually have cost functions that are regularly varying, but to networks that can compare their cost function to any regularly varying function. Okay? This is because the intuition is that we want to compare the one that our cost function looks similar to a function that is kind of regular when x goes to infinity. So how can we do that is for a network, the first thing is to compute a benchmark function, Cx, that then we will use this benchmark function to measure the regularity of all the of the cost functions in the network. So we choose this benchmark function, and then for each edge we compute the edge index. That is simply the limit of when x goes to infinity of the cost function over the benchmark function. Now, since we restrict our attention to networks that have cost functions that are comparable to regularly varying function, we know that this limit exists, and this limit can be 0, infinity, or in between. When we have 0, it means that we call the edge fast. When we have infinity, the edge will be called slow and tight in the middle. Given the edge index, we can then compute which is the index of all the paths in the network. And again, we compute the index of the paths using the maximum edge index that belongs to that path. What is the intuition here is simply that we want to capture the bottleneck of that path. Okay? And again, the index of a path will be fast, low, or tight if the corresponding index will be 0, infinity, or in the middle. And after we have the index of all the paths in the network, we can finally compute which is the index of the network itself. That is the index, the smallest index among the path index. This is because most of the traffic will be routed through the fastest path in the network. Having that, we can then say that the network is tight if the index of the network is between 0 and infinity, with the extreme excluded. Okay. And this allows us to say that for a single OD pair network, when we have a single OD pair network, when the traffic goes to infinity, if the network is tight, then the price of anarchy goes to infinity. I want to emphasize that in order to have that, is it enough that the cost function can be compared to a regularly varying function? And it, again, allows a broad class of cost function for our congestion game. Because, for example, polynomials are comparable, logarithmic functions are comparable, but also functions that are not regularly varying themselves, like exponential function, can be compared with a regularly varying function themselves. So you may use this notion for a very general class of congestion game. Now, as a direct corollary of that, we know that networks with polynomial cost, the price of anarchy always converges to 1 as the traffic goes to infinity. Now, I just want to mention that these were the weakest result in our work. Actually, the same result are realized when we have many OD pairs and variable demand in the different OD pairs. So when and the same assumptions, just you have to make some other assumption about how the different behavior is the behavior of the different OD pairs, but it's nothing that restrict too much the class of game that I described to you. So those assumptions are enough to guarantee that the price of anarchy converges to 1 in a general graph with many OD pairs and general cost function. So just to wrap up, and answer the question that I posed at the beginning of the talk. What is the cause of the congestion? And quoting Jane Jacobs, the traffic congestion is caused by vehicles and not by people themselves. Indeed, the price of anarchy converges to 1 independently of the topology of the network and independently of the number of OD pairs that you have in your network. So any tolling procedure, any way that you can think about of rerouting the vehicles in your network are not enough to improve the congestion that you actually can experience in the network. Thank you.
Time for questions.
Do you have an understanding of, let's say, the function of price of anarchy as the load, even for some sort of like very restricted examples? So in some, you gave the pathological example where you had like an exact description of the function, but what about like non-pathological examples where you know the two limits are equal to 1? Can you actually, under some restricted assumptions about, let's say, the topology, provide the actual function of price? Let's say, have parallel links and, with, let's say, polynomial functions. Can you give some sort of like, how does the price of anarchy as a function of the load in this network like look like?
So what we proved is that in such network at the beginning, before the traffic starts to be not negligible, the price of anarchy is to 1. And actually, in the paper we have results about the rate of convergence of the price of anarchy to 1, and the convergence is polynomial in terms of the rate of the traffic.
Yeah, I guess I'm asking the orthogonal question. So like, I understand like you understand the two limits.
Yeah.
But can you say anything about the shape of the function, even for a very restricted example? Like, let's say even for like two parallel links, like the Pigu example. Have you created like this?
When this, I mean the function, the shape of the price of anarchy is something that has one peak and then start from 1, has one peak and then goes back to 1. This is for the example that you mentioned.
Yeah, exactly.
And the shape will change for every example in the intermediate region because it will depend in the network topology.
Right, but for example, like, would you conjecture that at least for parallel networks it's single peaked? Or do you have any?
Actually, we didn't explore this there. We started, and yes, we agreed with this conjecture, but we didn't. We don't have any result on that.
I like your conjecture. Right, thank you.
Any more question? Yeah.
So in your case, so as the demand goes to 0, that is light traffic, and as demand goes to infinity, that is high traffic, right? Like, is
light traffic is when goes to 0, and heavy traffic is when goes to 0.
Yeah. So these are like asymptotic. Is there a possible way to say that if demand is less than, let's some alpha, we treat it as light traffic, and if it is above that, it is heavy traffic? Rather than just
yes, but I mean, you can compute this threshold, but they are in order to have those thresholds, you have to analyze the network a bit deeper. So you need to explore other properties of the network. So we did that for example, we have specific threshold for a Pigu example with polynomial cost. We have that in the paper, and we computed in that the rate of convergence for general network with polynomial cost. But in order to have specific threshold for general case, specific threshold are specific to the network, so you cannot have general threshold.
Okay, so in the interest of time, let's thank the speaker once again.
Hi, everyone.
Okay, so let's welcome next speaker. Its talk is going to be on routing games over time with FIFO policy.
Thank you. Hi everyone. So I'm going to present routing games over time with FIFO policy. So you know that routing games are well motivated by packet routing and road traffic. The most famous model is static routing game. So you are given a network. Every agent decides a route from his source to his sink, and the cost for using every edge is often an affine function of the number of agents using that edge. Such static models allowed for many good results. We know that those games are often potential games, so best response dynamics converge to a pure Nash equilibrium, and the price of anarchy is often constant. However, it's a static model, and it really lacks temporality. Everything happens as if every agent uses all the edges on his path at the same time. For instance, if you consider this network, agent 1 goes from S1 to T, agent 2 from S2 to T. In the static model, it implies that the congestion on edge UT is 2. And if you consider time, agent 2 reaches node U at time step 5, which lets plenty of time for agent 1 to cross edge UT before agent 2 arrives on the edge. So time-wise, the congestion on edge UT is never more than 1, which is different from the static model. In this work, we consider routing games over time with FIFO policy. So you are still given a network. Every agent still decides a route from his source to his sink. And for every edge, E, you have a capacity CE and a fixed delay DE, which can be depicted as the width of the edge and the length of the edge. Every edge also has a waiting queue, and we are given a tie-breaking order on the agents. So costs are defined as follows. For every edge at a given time step T, the agents who arrive on the edge are lined up in first in, first out waiting queue, time-wise. And then the edge lets in the CE first agents who traveled for DE time steps. The total delay for an agent is the sum on the edges of his path of the time he spends waiting on every edge plus the fixed delays. And when several agents arrive at the same time on the same edge, they are ordered with respect to the tie-breaking order. So strategy sets are paths, and we use the standard definitions of best response, pure strategy best response, and pure strategy Nash equilibrium. In routing games over time with FIFO policy, a pure strategy Nash equilibrium may not exist. Here you have 8 agents. The sources are squares and the sinks are diamonds. Agent 1, the pursuer, and who goes from here to here, and agent 2, the evader, who goes from here to here, they both have 2 strategies, either going up or going down. And the other agents only have 1 strategy. Agents 3 and 4 induce a positive externality of the evader on the pursuer for deciding the same strategy. And agents 5, 6, 7, 8 induce a negative externality of the pursuer on the evader for using the same strategy. So the pursuer wants to play the same strategy as the evader, but the evader wants to play a different strategy. So you cannot have an equilibrium here. That an equilibrium is not guaranteed to exist sets a typical research agenda in algorithmic game theory. So ultimately, we would like to know what is the complexity of deciding, given a game, if an equilibrium exists. So first, we define a Dirac-Style algorithm which maps path profiles to agents' delays. So it's a well-defined game. And then we study the complexity of deciding a best response, of computing a best response, and also of verifying if a given path profile is an equilibrium. All these three problems will turn out intractable or very intractable. So, in consequence, since rationality is not so well grounded because of this intractability, I introduced maybe more natural solution concept where every agent at every vertex retrieves instantaneous congestion data from the other agents from the past step. And given this data, it defines the costs on the graph, and they compute their shortest path according to this congestion data from the previous step. And in this context, I study the worst case loss of efficiency. These three articles are the closest related work. This model was, in fact, first introduced in atomic routing in a deterministic queuing model. They use a slightly different model where agents have a bottleneck objective on the path. But in their appendix, there are results concerning some of the edges of the path for individuals, like non-existence and NP hardness of verification. In general, what arises from this literature is that pure strategy in Nash equilibria are often not guaranteed to exist. Computing a best response is usually NP hard, and computing an equilibrium is also very intractable. But usually the symmetric case is tractable. So let us start with the best response problem. So given a game, I'm agent I know the adversary path profile, and I would like to compute a best response. It's a path problem. A good rule of thumb to know whether a path problem is computationally tractable or intractable is whether you can have Bellman's principle or whether you have preference inversions. When you have Bellman's principle, locally dominated solutions combine into overall dominated solutions. But when you have preference inversions, locally optimal solution may combine into overall dominated solutions. And so, for instance, here on B, you prefer using the upper path, but when you are on C, you realize that it would have been better to use the lower path. And it occurs that in routing games over time with FIFO policy, we can construct Dutch preference inversions. Here, when an agent crosses the trigger edge, many things happen, and it induces massive congestion on the bound edge. So you think you have a good path here, you use this good path. Here you had a long path, which would not trigger the bomb. So locally, you prefer the upper path, but overall, it would have been better to use the lower path. It's a preference inversion. And we will use it to show the NP hardness of computing a best response. We start the reduction from problem minimum vertex cover. So you are given a graph and you want to find a minimum subset of vertices such that each edge is covered by one vertex. Then we construct a path problem which models this problem. So on the path problem, you decide if you take each vertex or not. And you want to punish the fact that an edge is not covered, and that's where you use the backfires. For instance, here, if you have an edge between 2 and 4 and an edge between 2 and 5, not taking 2 implies that you are heavily punished for not taking 4 because you don't cover an edge, or for not taking 5 because you don't cover an edge. This reduction is also approximation preserving, so it is APX hard to compute a best response. And also, computing a best response reduces to finding a deviation. So the problem to verify if a path profile is an equilibrium is co-NP complete. We can show a stronger inapproximability result with a reduction from minimum coloring. It is NP hard to approximate a best response within number of nodes to the 1/6 minus epsilon, or within number of agents to the 1/7 minus epsilon. Since verification of path profile is a co-NP complete problem, the existence of an equilibrium problem nests a co-NP complete problem inside an NP problem. And indeed, we show that deciding whether a pure Nash equilibrium exists is complete for the second level of the polynomial hierarchy, which means that it is very intractable. We start reduction from problem max-min vertex cover. So you are given a graph which vertices are partitioned in a sequence of pair of parts, and you are asking whether whatever the sequence of subpart or vertices I take, the induced subgraph contains a vertex cover of size at most kappa. With this construction, it can be shown that it is a question equivalent to whatever the path profile that exists in individual deviation from the path profile. So computing, deciding whether a pure Nash equilibrium exists is very intractable. So even approximating best responses is is inapproximable. Even approximating best response is intractable. Computing a Nash equilibrium is very intractable. So rationality is not so well grounded here. That's why I proposed a model where the agents at every vertex, so it's really inspired by how you use Google Maps. At every vertex, you download instantaneous congestion data. Here, it's the congestion data from the previous time step. And it defines the costs of your graph, and you compute the shortest paths according to those costs. And in that context, I define a price of GPS, which is a worst-case loss of efficiency when agents behave according to their personal navigation assistant. And things can turn out really bad. In this example, you have an inner cycle and an outer cycle. The agents on the inner cycle have to cross the outer cycle to reach their outer sink, and the agents on the outer cycle must cross the inner cycle to reach their inner sink. The example is completely symmetric. And in this example, it happens that the agents from a cycle receive congestion data from the other cycle, such that procrastinating the decision to cross the outer cycle is not discouraged. For instance, here, agent I1, he could reach his outer sink from node V00 or from node V10. According to the congestion data, both paths are equivalent, so he may procrastinate his decision. So in the worst case, we have an infinite price of GPS. To conclude, I have shown that best responses are NP hard to approximate, and that deciding whether pure strategy Nash equilibrium exists is complete for the second level of the polynomial hierarchy. And I've also shown that when agents use their personal navigation assistant, it may cycle infinitely. Future work includes studying the symmetric case. In this literature, the symmetric case simply means having the same source. That's all. Because it's usually more tractable in that case. And maybe finding structures of network where the price of GPS is low or where an equilibrium may exist. And also, in this work, the decided paths are static. The costs are computed with respect to time, but the decided paths are static. It may be interesting to study models where the complexity of models where at every vertex they recompute their path. But subgame perfect Nash equilibrium may be more relevant in that context. Thank you for your time.
Time for questions.
I have a question about your example showing that pure Nash equilibrium do not always exist. There, you sort of like gave an interpretation of pursuer and evader, but somehow, in your model, everybody's trying to like minimize, some sort of like notion of congestion with these like queues.
Yeah.
So can you encode? It's not clear to me why you can encode the, pursuer-invader relationship through congestion costs. Can you give some sort of like insights about that?
Yeah, so when I was saying positive externality, it was indeed meaning a lesser cost. We can, so it's written in the paper, everything translates in terms of cost. For instance, here, the pursuer arrives at this point at time step 11.
So let me understand. So you have some edges whose like costs go down as the.
That's it.
Okay. Do you know? Okay. Do you have any sort of like counterexamples in the case where say all the costs are increasing?
All the costs are increasing.
Let's say if all the costs are like linear or polynomial, and you still have some like queuing system. Do you still have examples where no pure Nash equilibria exist?
So here we have FIFO waiting queues. FIFO waiting queues, they taste somehow like affine functions, because when you arrive, the time you spend on the edge is like the number of agents that are in the waiting queue plus a constant. That it smells like constant affine. So, and then I'm not sure to link this with functions on the edges.
I guess if you only have like negative externalities, Do you have an example where you still have like there are no pureness equilibria?
That's my only example so far.
Thank you.
It's worth looking.
So, I mean, so in this model, for your bad examples, do you need the capacity ever to be larger than 1? I mean, I'm like supposing a to model where all the C's were 1 and the D's were all 1.
So the D's were not all 1 here.
But I mean, but the D's shouldn't matter, right? I mean, you can just put a bunch of edges in series.
In terms of complexity, they do matter. You cannot like cut them into 1, 1, 1 because it would make like a pseudo polynomial reduction. Then it is true that I almost only used capacities equal to 1 in the reductions. So yeah, what's your point?
No, I was just checking. Like, what is the simplest model for which these negative results hold? That's all.
So yeah, I'm quite sure I can get rid of this capacity 2 here. So I think here in this example we can assume that the capacities are 1, and for the complexity, so at some points. Maybe there are very large capacities and capacities 1. I don't want to say more to be precise.
Okay, thanks.
Okay. Any more questions? Okay, so let's thank a speaker once again. All right. So this brings us to the last talk of this conference. It's on non-homogeneous Kleinberg's small world model.
So can everybody hear me? Okay. Hi everyone, my name is Fang-Yi, and I'm very honored to be the last talk in this wonderful event. And I'm very happy that you guys are still here with me. And so today I'm going to talk about non-homogeneous Kleinberg small world model, Cascade and Myopic routing. However, the routing part is quite different. So, this work is joined with Jie Gao and Schoenebeck. So what is a social network? Social network is basically trying to use the graph to model how people interact between each others. And in social networks, that even though people can behave freely, but the social network as a whole sometimes will show very special properties. And social network analysis is trying to come up with a model and doing empirical research to uncover those patterns in the social networks. So in this talk, I will revisit a classical property of social network, small world property, and review some classical result on that and what we have done on these properties. So it starts with a famous experiment conducted by Milligrams in 1967, which is pretty old. And in this experiment, Milligrams randomly picked several people in the United States to be the starters in this part, and pick persons in both sense, United States in the right top. Then he sent an envelope which encodes some basic information of the target to those starters, and those envelopes contain some basic information about the starters, such as their last names, address, or the jobs. And if the starters did not personally know the targets, then the starters is asked to pass the envelope to a friend or a relative who was more likely to know the target. So the envelope will pass in this kind of social network, and hopefully you will reach the target eventually. And the result is pretty surprising, even though that most of the envelope didn't reach the target. But among those which reach the targets, the average number of transitions is very small. It's between 5 and 6. So this kind of implies that there is this short path between all pairs of agents. So sometimes these were called 6 degrees of separation. And a natural question we want to ask is that can we come up with a simple model that kind of exhibit this short diameter property, but also show that a lot of clustering effect in the social networks. So Duncan Watts, Steven Strogas, and Mark Newman, they kind of come up with different variation of small world model, which go as follows. So they assume the people can be embedded into some geometric structure, such as a k-dimensional grid or ring. And we have strong ties. We will build our relationship with our neighbors, our relatives, so we will connect to the people that nearby us. And we will also have some weak ties, such that the people we meet in a conference or the people we meet in an airport. So we will have some random connection to the peoples in the world. And they show that these kind of simple models have very small diameters, but also you will have a lot of triangles in these social networks. So can we infer more from the empirical results? Kleinberg in 2000 noticed that actually these small world experiments might tell us more about the social networks. Notice that during the routing process, the starters or the middlemen, they cannot understand the whole structure of the social network, but the routing is still possible. So it kind of saying that actually the social network can support decentralized routing. That is, we can use very limited information, like the information of the target and the information of our neighbors, and we can still achieve the routing process. So I will call it Small World Model 2.0, which go as follows. So based on this observation, Kleinberg proposed a small world model called Kleinberg Small World Model. So it's pretty similar. Everyone is on some k-dimensional grid or torus. And we will have some strong ties, similar to the previous one. And the magic happens in the weak ties. They assume that there is a spatial parameter gamma, and the weak ties, the formation of the weak ties were related to the distance between the agents. So the probability that U and V making connection were kind of proportional to the inverse of their distance to some non-negative number gamma. And this gamma will be very important in their models. So to give you some idea, if gamma is equal to 0, then these models would reduce to Newman-Watts small world models. And if gamma is some positive number, for example 2, then we will see that the chance that U and V making connection will decrease as D increase. So here is another example. If your gamma is very small, close to 0, then the weak ties, the red edge is going all over the graph. If your gamma is very large, then we will only prefer a short range connection. So the red edge is pretty short in the large gamma case. And in this model, Kleinberg shows that this decentralized routing is possible. And when gamma is equal to 2, he proposed a Myopic routing. So it goes as follows. From the starter, he will pass the envelope to one of his friends, which has closest Hamming distance to the targets. And this process will iteratively until it reaches the target. And he proved that this routing algorithm is very fast when gamma is equal to 2. Moreover, if gamma is not equal to, for example, if E is smaller than 2, then he proved that any decentralized routing algorithm will not work. So, for example, this is the shortest path between starter to the target. And if you do the multi-routing, then you are using the purple edge there, which seems good in the meiotic sense, but in fact it will incur larger cost in the routing time. If gamma is greater than 2, then the weak ties is just too short for you to make a big jump in the graph. So in summary, if gamma equal to 2, then your routing time will be polylog. If your gamma is not equal to 2, then your routing time will be polynomial. So it kind of saying that the decentralized routing algorithm in the Kleinberg model is having very small window to work. So if your gamma is equal to 2, then routing is possible. But if it is 2.1 or 1.9, then it is impossible in Kleinberg's model. The second concern is that this model doesn't capture the diversity of the real social networks. So for example, this girl might have a smaller gamma, and she will prefer to making a long-range connections. He will not concern about the distance between their friends. And some people in the right part, which might have a larger gamma, which will prefer to connect to someone which is closer. And in social network, we will expect that people will have different kinds of ways of making relationships. So can we come up with a small variance of the small world model, which has both this property, but also shows the diversity of the social networks? So this is basically our model. We'll propose a non-homogeneous Kleinberg small world model, and we will try to understand how does the multi-routings or contagions change in these models. So recall that the Kleinberg small world model, the weak ties is sampled from these magic ways, and our complaint is that the gamma shouldn't be, everyone shouldn't have the same gamma. So it's quite straightforward to replace that into a gamma U. Everyone will have their own gamma, and we assume this gamma is drawn from some distribution. So this model will be characterized by this distribution D. And we want to ask, okay, so given this distribution D, it will contain the previous Kleinberg model as a special case. Because if your D is a delta function, then it's the original Kleinberg. If your D is a kind of a noisy version of a Gaussian or some different distribution, then this will support different kinds of way of making friends. So let's go into our theory. So the theory is quite straightforward. Okay? So given your distribution D, and this is your probability density function, then we show that if you have concentrated probability mass around 2, then your routing time will be polylog, very fast. On the other hand, for the lower bound part, we show that if there exists some open interval containing 2, then and the probability mass in this open interval is 0, then your routing time will be polynomial. More specifically, if the window size is kind of 2 epsilon, then your degree of polynomial depends on the epsilon. And moreover, we also prove that we don't need a lot of probability mass around 2. It's sufficient for us to have non-neglectable probability mass around 2. So if you have some, if your distribution can be lower bounded by some polynomial with some degree alpha, then your routing time will be still polylog. And these two things kind of have give a pretty complete characterization of the routing time in these non-homogeneous models. So right now I'm going to tell you some my proof outline, which I think is pretty entertaining, so bear with me. So if gamma is equal to 2, the original Kleinberg proof is basically measuring the progress of your routing algorithm by measuring the distance between targets and your current position, the position of your envelopes. So he basically draw log number of disks centered at the targets with the radius equal to the power of 2. And for the upper bound part, we can just replace these calculations by integration, and you can show that the chance of jumping into a next smaller disk will be pretty large. Then you can get a polylog routing time. And the interesting part is in the lower bound. So in the original Kleinberg model, if gamma is smaller than 2, then they show that it is too random to jump into a very small disk. Okay. More specifically, the disk size, if the disk size is n to the epsilon over 3, then this will be too small for your weak ties to jump into that. Okay. So this gives the lower bound for small gamma case. And if your gamma is greater than 2, then the original Kleinberg proof showing that it's impossible for you to make a big jump. So this is the parameter of layer. However, in our non-homogeneous Kleinberg setting, we can have a mixture of both large gamma H and small gamma H. So layer low bound is kind of not working if you just apply them, because you can use the red edge in the early phase and you use the purple edge in the later phase. So to prove our theory, it's basically based on a simple observation that the probability that for you to jump into a small disk depends on two things. One is the distance between your point to the disk center. The other is the size of the disk. And if you combine these two things and do more careful calculation, it's kind of pretty delicate, but if you do a more careful calculation, then you can prove the lower bound part. So finally, for the complex contagions part, we show some theory which is pretty similar to the multi-routing, which is given your distribution D, then we kind of give you extension about the original Kleinberg small world model applied on a K-complex contagions model. So I will skip here, and thank you for your listening.
Time for questions. Okay, if there are no more questions, yeah. So let's thank the speaker once again.
I would like to make one last announcement for Wine 2017. So we have the Tempo Travelers waiting for all of you. Whoever has signed up for Shri Sagar Masala Dosa, you're requested to go there. The transport will be starting in the next 5 minutes or so, because the appointed time in the